Good morning, everyone. We still have half an hour before noon sets in. My name is Josh. I'm part of our Morrison Planetarium presenter team at the California Academy of Sciences, and I am delighted to be here today with our manager, the head of our engineering department, our own extraordinary engineer, Dan Tell.
Hi there.
So, Dan, looks like you might actually be at the Academy right now. I can see some of our engineering stuff behind you.
Yeah, I actually am at the Academy. Of course, the Academy is currently closed due to the ongoing COVID-19 pandemic. But yeah, for engineering staff like myself, this is providing us actually an essential time where we can do a lot of maintenance on planetarium systems. So we're doing a lot of stuff around security remediation, maintenance on projectors and computer hardware that often, we squeeze into about 6 days a year. Morrison Planetarium is only closed for six and a half days a year. Which gives us normally a tiny opportunity to do an enormous amount of maintenance we have to do on our projectors and computer hardware. So yeah, we're making the best of this time and catching up on things we can so that when we do reopen, Morrison will look better and work better than it ever has.
That's good to hear. I'm excited to return. Are you keeping 6-foot spacing between you and O'Brien behind you?
Apparently. Yeah, I can't in touch.
Okay. So, Dan, you were going to show us some of the cool stuff that you work on at the Academy, kind of your bread and butter for making visuals for our dome.
Mm-hmm.
So can we switch over? Oh, yeah. We got a cool thing right there.
Yeah. So I want to dive into, this will be, I guess, a little bit more of a behind the scenes than a lot of the cosmic conversations have been to this point, and talk about how we actually get data and content into the planetarium for you, the audience, to enjoy. Or for you, our presenter, like you, Josh.
We enjoy it too.
But I also want to credit, I will be talking about this, but this isn't just work I've done all on my own. Planetarium engineering is a team. A lot of content was added by my colleague Matthew Wren, our colleague Milan Bott, who left a little more than 2 years ago to go join Apple instead of work here, as well as our visualization studio engineers, John Britton and Autumn Moore. So it's a team. All of this would not be possible without the work of many, many people.
They do some amazing stuff.
Yeah, and I'm really lucky to work with such thoughtful, creative, insightful, amazing people. So we're starting off here at the Hubble Space Telescope, hopefully a familiar...
Pretty iconic.
Point. Yeah, probably the most famous of all the space telescopes to the public, but not our only one. We have, it's got to be dozens of different space telescopes up there by now. And this is where I want to start talking about how we bring data and information into our software. If you've ever been to Morrison Planetarium, we sort of have two components that make up most of our planetarium shows. We have the amazing pre-recorded content put together by our visualization studio that forms the narrated part of the show. Like when you come to the Morrison, you hear George Takei talking or Sigourney Weaver. That's the pre-rendered work of our visualization studio, which takes them, 1.5 to 2 years to produce a 20-minute show. Because they're putting so much work into making this perfectly mastered product. The other side of what we do at Morrison Planetarium uses our real-time systems, which are what we it's like having a video game playing on the planetarium dome. It's an interactive, live-generated, real-time 3D interactive simulation of the universe. And this is something we are constantly updating and adding to. And if you've ever been to one of our shows and George Takei stops talking and someone like Josh or one of our other presenters that's when they're switching over to the real-time software, which we often use to give a slightly less polished, but still data-driven update to the science story that you might have heard in the primary show. We also use this for other one-off shows. We use it for our live tours of the universe that we do towards the end of the day, as well as specialty programs like our nightlife programming, specialty shows for students. It gives us a lot of versatile strength to tell different stories and incorporate data faster than we can into our pre-rendered shows.
A lot of flexibility if you don't have to take 2 years to make a show.
Right. So yeah, speaking of that flexibility, here we are at the Hubble Space Telescope, and this is an example of a model that we brought into the software. So the software is a simulation of our universe, and it is as complete as we can make it and as our computer can store information. This Hubble model actually dates to a project we did with the Kennedy Space Center in Florida, which you might know is where they launch most of our rockets from. Mm-hmm. They installed a 3D theater that uses the same software I'm using right here, UniView, currently owned by the Zeiss Corporation, who invented planetariums about 100 years ago. And this is a case of where we got to, I think 3D models are one of the most approachable forms of data that you might think of us as bringing in, because...
especially these days.
Yeah, a 3D model, I mean, it's tactile in a way. It's a representation of a real, tangible thing. And
Hmm.
like everything, when we have a model in our software, we try to make that as accurate as possible. And especially because this was for a project we were collaborating with the Kennedy Space Center on with about Hubble, we had to make sure it was as accurate as possible. And so that's where it gets into the work. We built this model in the open source 3D modeling software Blender, and you can see here I've sort of rescaled it so it's a little turned off. But we use these source elevation drawings of the spacecraft itself to build an accurate representation of the model as closely as possible to the real thing, so that we can really show people what they would want to see in the universe, what they would expect to see. Try and make things as accurate as possible to tell meaningful, accurate, complete stories.
We had a question pop up from Dan St. John wanting to know if Hubble is just lucky that it hasn't been hit by anything. It's not that far away from Earth. It's only about 225 miles up, as Dan's showing us right here. So it doesn't have its protective atmosphere wrapped around it, but there's also not that much stuff which is going to be cruising through this neighborhood. So it's more than lucky. It's unlikely that it's going to get hit. Plus, we keep a pretty close eye on it.
In a second, too. That might give us some perspective on that.
Mm-hmm.
But yeah, whenever we show a model like this, we try to have it as accurate as possible. So we're talking about something as close to the real thing and giving people as much as possible the experience of really seeing these things, really seeing the data, and especially talking about it on a human scale. I think that's one of the things we do really, really well at Morrison Planetarium is whenever we calibrate things in space or even time, we try to calibrate it in something that's appreciable to human beings, because that's the whole point of everything in astronomy. It's not just some abstract science. Astronomy is us asking sort of these fundamental questions about why we are here, how we are here, why is there something instead of nothing? And all of that is a human story, because the unique thing about being human is we are the universe's way of introspecting on itself. We're the only living thing we know that is capable of that. And so all of these stories about us trying to learn more are stories of that. And so with Hubble, it's very easy to compare. Hubble's about a 2.3 meter diameter mirror, which is ever so slightly larger than a human being. So
depending on the human being, but sure.
Depending on the human being, right. It's true. Some people might scrape that, and some people are a bit below.
Well short of it.
Yeah. But yeah, when we're talking about that, so, it's like imagining that your eye was the size of your whole body. That's what Hubble is like. That's part of what makes Hubble so special. That, and of course, being above the atmosphere. And so using tools like this and using comparisons with 3D models, we can start to build out this human scale. And of course, as we move into space, the scales become so drastically disconnected from that human scale. So it's good to have something, I think, to always try to ground us at the beginning of any planetarium show or any virtual experience in the planetarium. And I think that's part of what planetariums do that is so special is, we have this experience in the language of immersive cinema. And of course, immersive cinema is becoming democratized through headsets and VR. But the planetarium is this unique, experienced environment for those topics. And speaking of things hitting Hubble, as we pull out, we can start to look at larger data sets. Hopefully, I have that loaded. Again, you're seeing sort of the behind the scenes of what the background data might look like as we would normally see it.
So Dan, you're looking at, it looks like a long menu there. Has a lot of the things that are stored inside inside UniView.
Yep. So yeah, here, for example, I'm turning on more of the satellites that we have around Earth. And this is accurately mapping the orbits of all the known satellites. And this gets into, why hasn't Hubble been hit? Well, the short answer is we know where everything is, including more or less, right? We have thousands of satellites. All of their orbits are tracked and monitored. And there are, of course, a handful of satellites that have actually collided with each other or have been destroyed by missile tests. And even the debris of those satellites we have to track so that we know where everything is in space, especially because, we have the space station up there with astronauts on it all the time. And JPL actively monitors where everything is and does occasionally move things out of the way of each other so we don't have collisions. Speaking of that accurate data, that gets into, a big part of what we do is talking about space missions, all the missions that we're using to explore the solar system, and something else that we try to do very, very accurately. So, for example, last week, if anyone joined us for the Cosmic Conversation then, we were talking about the New Horizons mission to Pluto.
It was a very fun one.
Yeah, this is, we have the solar system here in front of us. Blue lines represent the orbits of the planets. Of course, in space, you don't see the orbits. We do that to help ground you. And I've drawn this orange line, which is the trajectory of the New Horizons spacecraft. When we talk about stuff like this, when we do these trajectories, again, we're using the actual spacecraft data. In cases like this, we can actually go to NASA's own websites, their own tool sets. This is NASA's Horizons Solar System Dynamics Simulator. And from Horizons, you can request position and velocity and time information of almost any object in the solar system.
That's a lot of numbers.
Yeah, many of the space missions. And so using this data, we can assemble a trajectory using, again, NASA's own tools, like their command line tools, to assemble something that our software can read to give us the exact position of any spacecraft throughout its mission so that we can follow along and see these spacecraft exactly as they explored the solar system. We can go back in time. We can look at the Voyager and Pioneer missions exactly as they were flown, as they did flybys of the outer solar system and their moons. Or, as we're looking at here, New Horizons, it's flying on it as it explored Pluto. And this gives us, super high precision so that we can do these very accurate flybys of missions as they happen and really take you, the audience, on a journey to experience things as they are in our solar system. So drop in our model of New Horizons, and in the background we have Pluto and Charon, again, for these very high accuracy data-driven stories. And that extends, of course, beyond orbits, trajectories, and 3D models. It extends into how we talk about these bodies themselves.
Now, this is a historical view of where New Horizons was. As New Horizons flew up to Pluto and then past Pluto, we would still be able to show folks exactly where it is?
Yep. That's a live, accurate flyby. Second by second, it will continue to follow New Horizons. We can even draw that out in a second. But right now, and actually some of the data is loading in, we're looking at the data actually returned from the New Horizons spacecraft itself. And this allows us to have three-dimensional views of other planets. Something that's often said is, we have the surface of Mars mapped better than the floor of our own ocean. And that's true. We have a great wealth of high-resolution information about a variety of bodies in our solar system. And I think that's part of what the amazing power of the planetarium is we can use these high-resolution data sets to explore these planets in incredible detail and transform them from just dots in the sky or, maybe a pretty picture you might see on your computer to a landscape, to a place, to a world where we can take our audiences to visit and explore and see it non-abstractly as this amazing place in space that it really is. And
I recall from the New Horizons folks saying that we have geology as we understood Pluto and how its surface changed over time.
Yeah. When we got to work with the New Horizons researchers, I remember one of them saying, when we got to Pluto, we were expecting to find elementary school geometry. We thought it would be a frozen ball of ice, not very exciting. Instead, we found high school level chemistry because Pluto's heart, as we often think of it, this great sea, you can sort of see its weird rippled texture and these hexagonal-ish lines cutting through it. This sea is a sea of frozen nitrogen ice, which, as they report, sort of has the consistency of like toothpaste. So it's like a gigantic sea of toothpaste. And these mountains sticking up out of it are mountains made out of extremely cold frozen water ice, frozen so cold it's harder than granite. And so
Hannah's asking, would you say this has oceans and beaches like Earth does or any other planet?
So no other planet that we know of has liquid water on the surface. But depending on how you think of oceans or beaches, you could say maybe. If we look up here in these among these ice hills of Pluto, we can see this figure, which is a little nitrogen lake on Pluto, currently frozen into solid nitrogen, but it has beaches around it in that sense. We could say we have beaches on other planets. If we were to take a detailed look at Mars, which maybe we can do towards the end of the show, Mars, we're almost certain, did once have oceans on it, and we can still see the remnants of that coastline in the data when we look at Mars.
Not quite a planet per Hannah's description, but I would argue for Titan as well. Definitely has sandy stuff and liquids, so that's as close to a beach as you're going to get.
Right, we have oceans of methane and beaches there, and we also have undersea frozen oceans on many of these bodies as well, including...
Hard to call that a beach, though.
Yeah, a beach there. So if I pull out from Pluto a little bit, looking at that planetary data, and by the way, that's data that again we are receiving from NASA. We're working with researchers to process and turn into something interpretable from the raw data. But something else we can do is sort of look at large data sets. So one of the ways we can talk about this is sort of like, well, often in planetariums, as we've had to for the last 14 years now, talking about why is Pluto not a planet? And part of that deals with like how we can now simulate things. And even when working with researchers, help them see things in their data that maybe they haven't seen before. We do a lot of programs with asteroid researchers because asteroids is a big topic of research. And let me just throw up a couple data sets nearby Pluto. So I've just turned on all these are what we call the trans-Neptunian objects, which is asteroids that have orbits beyond Neptune. Some of them cross the orbit of Neptune, but in general, their concentration is beyond the orbit of Neptune. And one special family of these objects are what we call Plutinos, which includes Pluto. The Plutinos, we can sort of see bracket Pluto on two sides. And they're famous for having what we call a 3-to-2 resonance with Pluto. So I prepared this simulation a few years ago when we had a planetary dynamicist talking about her research in the planetarium. And one of the things I thought was pretty incredible once we put this together, I'm going to change our time a little bit, is researchers don't always sort of look at the data in a visual form, or they might make animations, they might
graphs, some kind of representation.
Right, but they're not necessarily, actually, let me change that date again, not necessarily looking at data in motion in both time and space. And I think that's one of the incredible things that the planetarium can do. So I'm going to speed up time a whole bunch here and just show us how the Plutinos move. And what I thought is incredible as you watch it is you can sort of see, as Neptune swoops by them, they move towards the outer part of their orbit. As Neptune moves away from them, they duck back in towards the inner part of their orbit. And this process repeats in such a way that they go around twice for every time Neptune goes around 3 times, never intersecting. But stories like this, looking at data like this, tells us about how our solar system formed. Because, everything in our solar system is the leftovers of some cloud of gas and dust that everything was before. And in most of the solar system, asteroids like this got vacuumed up by the big planets. And from places like Neptune, we can see all the asteroids that have to cross its orbit are the ones left over that don't have a chance being hit by Neptune. They're all the ones that either through the influence of Neptune's gravity or just the luck of their initial position move out of the way of Neptune when it passes by so they don't get sucked up by the planet. And this is part of our, growing understanding of the solar system, not as this, static set of crystalline spheres as the ancients thought, but as a dynamic, changing environment. And the planets as just part of that evolution from tiny pebbles of rock up through stars of the objects that can form within a solar system. Other examples of that would even be like Jupiter similarly has these captured fields of asteroids called the Trojans. Slow time.
There's 2 little tufts of asteroids in blue.
Yep. Yeah, these sort of, someone once called them the ears of the solar system. But, these are these captured fields of asteroids that are basically captured in a place in Jupiter's orbit where Jupiter can't suck them in with its own gravity. But looking at them in 3D detail, actually, the last Dean lecturer we had before we closed for COVID was looking at this with me, and she was like, wow, I never realized, looking at them, the way they sort of bob up and down, the way they actually move in 3-dimensional space, such that these orbits stably move without being affected by Jupiter. So looking at these things in 3 dimensions with that time factor and that ability to freely explore in the planetarium, I think that's really cool. That's something that we benefit from. It's something that researchers benefit from.
Absolutely.
It's something that our audiences get to better benefit from to understand the universe in all 4 dimensions.
I've heard it called a theater of time and space, and I think throughout planetarium's history that's important. Dan asked, what is the chemical composition of what astronomers would call dust? I would say it varies tremendously, but it's pretty uniform in size. So we're talking about stuff that is the particle size of what we think of as smoke, but just hanging out in space. It could have carbons, it could have hydrogen, it could be all sorts of complex chemistry, but generally it's really small particle sizes at a very low density. A lot of the things we think of as dusty are about 1 atom per cubic meter. That's pretty low density. And Hannah's got another question. Why are the Plutinos surrounding Neptune specifically? What did Neptune do to offend them?
I mean, that's sort of by definition of, we have the 8 major planets, which have cleaned things up mostly. And these planets have these families of asteroids that are the leftovers that are affected by their gravity. Since Neptune is right at that edge of the major planet forming part of our solar system, there's a lot more asteroids beyond it that did not form into major planets. And the Plutinos is sort of by definition. Pluto was the first of these objects we discovered, but we've since discovered, hundreds of objects that have Pluto-like orbits, showing that they are controlled by the gravity of Neptune.
Well, Dan, before we get too far away, there was a story you mentioned earlier that I would really love to dive into, the Trappist System.
Yeah.
Would you be willing and able to take us there?
Absolutely.
Tell us a little bit about how we visualized it?
Yeah, this is another example of a great chance we had to collaborate with researchers. You've sort of been seeing me work in the software. I'm going to jump into the interfaces that we give our presenters to actually making the shows
easy. Very familiar view for me.
Yeah. So I'm going to pivot us around to look at Trappist. So Trappist 1 is a star identified by the Trappist Telescope Survey. It's a very long acronym, as astronomers like to make. But it is, and it is intentionally like a joke on Trappist.
Belgians, beer.
Yeah, exactly. So yeah, I've got this marker. It is a faint red dwarf star. You don't see the star in the night sky with just your eyes. But Trappist 1, was it 3 years ago now, really caught the attention of the astronomy world because it was this little red dwarf star around which we discovered 7 planets, almost all of which are about the size of the Earth. And not just about the size of the Earth, but also, I'm painting up this green area, 3 of them lie more or less in what we call the habitable zone. The habitable zone is the distance from a star where if you are about the size of Earth and you have an Earth-like atmosphere, your planet would be habitable. It would have liquid water on the surface anyway. I mean, there is obviously an object in the habitable zone of our solar system that is completely uninhabitable, the moon, but it has no atmosphere. So the Trappist system is really cool because this is a chance we got to collaborate with our close friends down at Caltech. So Robert Hurt and his team down at Caltech, who work with the Spitzer Space Telescope, did some basically collaborative observations of the Trappist system between Spitzer and Hubble. And Spitzer is an infrared space telescope. It sees heat. And so because it can see heat, it can look at these planets and tell us things about what temperature they are. And then combined with Hubble, we can do things like spectroscopy. With the measurements of other satellites, we can sort of put together their mass and their size. And because of that, we can kind of guess about what these planets are made of. And when we can guess about what these planets are made of, we can measure their density because rock and ice and water all have different density and gases. And that gives us this vision of we can make informed guesses about what these planets might look like. And that's what Robert and his team down at Caltech did. Using their data, these are data-driven hypotheses of what the Trappist planets might look like. And that's what makes Trappist so exciting, is it could be this other planetary system that could have oceans of liquid water. Also, you can see the planets are very close together. You can get really incredible
planets from planets.
Yeah, live on one of the Trappist planets. But yeah, these are worlds we know are some mix of water and rock. And therefore, there are chances that these could be habitable planets. These could be other places in the universe life could arise. So, of course, this is not what they truly look like, but it's an informed guess what they might look like.
We might not know the shapes of continents, but we could guess how much rock is there compared to water.
Right. And there are space missions in the future hoping to actually see what continents might look like on distant planets.
I hope I'm there to see it. But speaking of returning data, Naomi wants to know, how long does it take to turn data from the probe into something we can show to the public? I think Trappist is a great example of that.
Yeah, it totally depends on the mission. So in the case of that Trappist data, we were actually working with the researchers before the public release of the data to make sure it was available. The same could be said of Pluto. In some other cases, and let me bring up another data set here.
While Dan's grabbing that, when the Trappist data came out, the day of the announcement, we were able to take it to the floor with models Dan and his team had created and tell the public about something that was in the headlines with our presenters interpreting and flying to the solar system for museum guests, which was a really fun day.
So here I've changed our view to a sort of the dome planetarium view. You're seeing this circle, and pulled up a data set from the Gaia satellite. The Gaia satellite is a mission that's been operating for, I'll say, 5 years now, past the Earth, which is helping us to better measure the distances to stars, but also their motions. And so if I turn some time on, this is an example of a data set just like that, where we're working on a relatively fast timescale of return, sort of basically as the researchers themselves were coming through this data. And so this is where we collaborated with our colleague Jackie Fardy at the American Museum of Natural History in New York to take her work as she was pulling through this freshly released data just coming down from this satellite, to find stories to tell in it. And her focus especially is on young stars, stars being born, and how they sort of interact with each other. And we're looking at here what we call moving groups, which are groups of stars still living together from when they were born. Stars are born in these big clouds of gas and dust, and they're born in families. And for millions of years after they're born, they hang out together in these moving groups where all the stars continue to move together. And by teasing apart these moving groups, we start to learn the story of how stars are born, where they come from, where they're going, and even where we came from too. We're unlikely to ever find other members of our stellar nursery.
Don't say that. We'll find them one day.
Right. We're certainly hopeful, but we can still observe how stars and solar systems are born and how that tells the story of why there's something instead of nothing.
So this is a pretty big data set, but there are some even bigger ones we've thrown in, especially in terms of scale. And I got to say, I am very proud of what we've done with the cosmic microwave background.
Yeah.
Would you be able to take us all the way out?
Sure. So I'm going to pull us drastically across space, out of the Milky Way, out beyond the known local nearby galaxies, into increasingly large scale structure of the universe. And of course, when we look out into space, we're also looking back in time, because light takes time to travel. So, you look at the moon, you're looking at light that left the moon a second ago. And of course, it's reflected sunlight. You look at the sun, 8 minutes. You look at Jupiter, which is up in the night sky tonight, you're looking at light that's about an hour-ish old, maybe a couple hours. When we look out into the deep universe, we're looking at light that is millions and billions of years old. And so we start to see, galaxies spread out, and then beyond the galaxies, we see what we call quasars, active young galaxies that don't really exist in the modern universe. And if we go very, very far out, we see the first light in the universe, what we call the cosmic microwave background. The cosmic microwave background dates to about 380,000 years after the Big Bang. I think that's numbers right.
Can't go out of the universe.
Yeah. It really is. Before this light was emitted, the universe was so dense, there was so much stuff in it, that regardless of the fact it was still already very big, 380,000 years after the Big Bang, it was as dense as the inside of a star. You might have heard that it takes a photon thousands or millions of years to leave the inside of a star. That was the universe. There was so much stuff. Every time a photon was generated, it ran into something else and was reabsorbed. So 380,000 years after the Big Bang, the universe's density dropped enough that photons could freely scatter in space, and basically the lights turned on for the first time. And this is light that we can still see out in space. When this light was emitted, it would have been blindingly bright, of course, but it was the light that would have been emitted by a star that was about 3,700 Kelvin in temperature. If you've seen this data set before,
specific color we selected, right?
Yes.
So this orangey color, if you folks like your toast pretty well done and your toaster becomes this color while you're making it, your toaster is about the same temperature the universe was.
Yeah. The way we're visualizing this, it once again is sort of using guidance from our friend Robert Hurt down at Caltech. The way sort of the data was released was in this rainbow color scheme, in which...
That looks pretty familiar to some folks.
Yeah, whitish is sort of the baseline temperature, and there are fluctuations in this light of about 1/10,000th of a degree. On average, it was 3,700 K at emission, but there were fluctuations of 1/10,000th of a degree. In the original map, hot is red, cold is blue. So red is 3.0001 degree. Yeah, very tiny variations, but those variations actually gave rise to the whole structure of our universe. Here at Morrison, again, we want to tell relatable stories. Mm-hmm. We want to tell approachable stories. We don't think rainbow color maps always get across that story. And so we visualized it this way, again, with, sort of the guidance of our friends down at Caltech who work with infrared science. We are representing it as the color it would have been. Again, we're not blindingly bright and saturating your rods. And the variations instead are cooler are darker, warmer is lighter. And still to tell us the story, but again, tell us the story sort of as an exaggeration of what you, in theory, could have seen if you were actually looking at the universe billions of years ago. And of course, when we see this light now, it is no longer visible light. It comes to us now only as microwaves because the expansion of the universe has stretched that orange light out so much. It's very, very faint microwaves that we only really see as TV static now.
It's kind of a wonderful thing to imagine that the wavelengths themselves become stretched as the universe expands. So there's the cosmological reddening of it.
Mm-hmm. Yeah, the space itself is spreading out, and the wavelengths riding through space are getting stretched with the universe itself over billions of years.
Now, it looks like you're changing our software.
Yeah, before we run out of time, I did want to dive into another piece of software we use. I focus mostly on UniView, which is sort of this custom, as our planetarium director would often say, bespoke planetarium software developed just for planetariums. But I want to take a minute to show you a way you can do this at home. This is a piece of software called Open Space. It is an open source project that we are contributors to on a NASA grant. AMNH are the primary investigators and leading this effort, but it's working on making planetarium software not just useful for planetariums, but as an open source piece of software that anyone can download at home. And in fact, anyone can add or contribute data to. So, I was just looking at the Earth there very quickly, but this also contains a complete simulation of our solar system's major planets.
So for folks at home or in a classroom who want to check this out and do a flight, kind of like we do in our planetarium or like you saw Dan do today, this is a really powerful tool and a great way to check it out.
Yeah, and it's another case where we are always working to integrate new data, tell new stories, make a more complete picture of our universe. Open Space as is comes with a lot of great built-in utilities too. That Gaia data that we took a look at a small part of. There are custom Gaia builds of Open Space where you can really dive into looking at how the Gaia data is being handled and see the story of how stars move over time. Open Space is also really great. We were talking about high-resolution planetary data.
Taking us into Mars.
I'm going to take us into Mars because, Open Space, again, one of its great strengths is doing this thing that I love so much of turning these planets into worlds, turning them into real places, because we have Mars mapped in incredible detail.
Except for that part.
On most of Mars, we have the planet mapped down to about 6 meters, so about 18 feet per pixel resolution of a camera. So, if you walk across a room, that's 18 feet. We have the surface of Mars mapped that good. And in many places, we have data on Mars down to 1/3 of a meter, 1 foot resolution. So you can look at Mars like you're looking out of a second-story window of your home. I haven't sort of like preloaded this data for a smooth flight, but
it's cool to see it loading in.
Yeah, it's as it's loading in from sort of the web servers that store this data, because this data is gigabytes and terabytes of data to represent the whole surface of a planet in this high of detail.
Can you tell us a little bit about the stripes we're seeing?
Yeah, these stripes are actually the camera passes of our orbiting spacecraft, the Mars Reconnaissance Orbiter. So that's our spacecraft that takes the pictures. It is a satellite. We actually have a whole constellation of satellites orbiting Mars.
Soon to be one more.
Yeah, soon to be a couple more. So basically, as it passes over Mars, it travels at an oblique angle, and that pass it makes as it's flying over, going snap, 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 taking pictures. We get that data as these stripes of data across the planet. And in addition, it's also measuring the altitude of objects on Mars. And we can also, NASA Ames has what they call their 3D stereo pipeline for interpreting that data. So we can see Mars in this kind of detail, not just the imagery, but also the terrain. So once again, talking about visiting these things as real worlds, as real places, as evocative places in the universe. And hopefully that gets into the whole point of what we're doing in the planetarium. I like to believe the point of a planetarium is more to inspire than to educate. we often have audiences for 25, 30 minutes at a time. You can't teach people everything about the universe in 25, 30 minutes. I can't even do this
much as we try
in 25 minutes. But I think the whole point of the planetarium is to create an inspirational environment, an environment where we give people a taste of how amazing the universe is and encourage them to go on and study and explore more on their own. So if we can create these inspirational moments, and then you at home can go and access the same data and dive in it in detail, and especially for young kids and teenagers and people sort of looking for, we all have this natural curiosity. Why are we here? Why is there something instead of nothing? But especially for young people who are at the point of their life of figuring out, what am I going to do with my life? How will I seek out my answers to these questions? How will I contribute to human knowledge? Hopefully this gives you a way to see how data itself is managed and pulled in. And even as you grow up and look for career opportunities, how you can become a contributor to our research and understanding of the universe. And absolutely the most rewarding part of the job. It's exciting to get to work with researchers and see this new data, be one of the first people to ever stand on a ridge of a mountain on Mars or on Pluto and look across it. But the really rewarding part is when we get to hear back from people who came to the planetarium as a child or as a teenager, and it changed their life. It made them decide to go into some form of research or art or anything where they, either through imagination or curiosity or research, expanded human consciousness out into the universe.
Seems like there's some very profound lessons we all can learn from that kind of wide view. So, Dan, a little bit of a question for you. You came to planetariums because of that same kind of inspiration, right? Not because you had a PhD in astronomy and decided this is the career you wanted?
Yeah. I was very lucky to get involved in informal science education, really through volunteer and internship opportunities in middle school and high school. Volunteering with a nature center, volunteering and interning at a museum. It was actually a local history museum with a planetarium focus, the Grand Rapids Public Museum in Michigan. A really great planetarium. And yeah, I love the subject. I love the work. And obviously I come to it sort of from the technical side. Planetariums use very unique hardware and software. And I love solving problems. And planetariums, because it is such a unique combination of, there are companies that, of course, sell planetarium systems, but we're using off-the-shelf hardware developed for other purposes. Mm-hmm. We have a few pieces of software custom developed for planetarium purposes, but everything's very unique. So there's a lot of problems that we get to solve. And that's what I loved about it so much, working with these really weird pieces of technology and getting to solve problems in unique, new, fascinating ways. Like showing that trajectory out to new horizons or this high-resolution map data. These are problems that we have been solving in the planetarium field in unique ways of how to visualize them in just the last handful of years. Mm-hmm. The very engine that allows us to ingest this data was developed by a partner of the software developer Illuminati, only some 15 years ago. And we really only figured out how to host and manage this data ourselves within the last 8 or so years. How to build these trajectories for spacecraft and missions are all things we've sort of been figuring out of whole cloth so that we can tell the best stories possible. And we're continuing to always find new ways to ingest and process data so that we can tell these stories and tell stories without the limits of technology. I think that's the important thing about as planetarium technology advances, mm-hmm. the technology should never be the star of the show. That's my opinion about all kinds of things. The technology should be invisible, and it should give you this gateway into an experience without any limits, without any restrictions, allowing our audiences to see and go to places seamlessly. That's the beauty of this kind of technology.
Well, you've given a huge amount of storytelling power to me and my team, and I think we thank you immensely for that. Dan had a question about, do we have access to other countries like China's satellite data? We, as an astronomical community, there's a ton of data sharing. While different countries have different rules about how long it might take for their researchers to process information before it's shared with the rest of the community, it changes. But we ourselves have benefited from European Space Agency missions, from international collaboration missions, and from hosted missions from other nations that share their data with us.
Yeah, with China in specific, there are some treaty restrictions on some kinds of information being shared. A lot of actual spacecraft data is actually heavily restricted to prevent international exchange of that data. But the resulting data from space missions, generally researchers are about open information, because unless we all have this complete picture of the universe, we can't build upon other people's research. We don't want to repeat research. We want to keep growing, keep building. So an enormous amount of the data compiled by astronomy researchers is shared. So when we're building data sets, we can just go to these websites that host these shared data sets and pull information, not just from NASA, not just from the European Space Agency, but from private researchers all around the world. There are also, specifically to some of China's missions, there have been some unique data sharing going on with the results of those missions lately. One of our other partners down at NASA Ames, if you go to NASA's Moon Trek website, which allows you yourself to be able to explore high-resolution terrain data of the moon, one of the most recent data sets they have added is information from the Chang'e 4 satellite, which has mapped the moon, I think, in basically meter per pixel resolution. So you can load that data set up in Moon Trek. I'm not going to do it right now. I want to dive through the menus. But look at this brand new photographic map of the moon from Chinese satellites.
So it sounds like there's a ton of tools out there between Moon Treks and Mars Treks and a bunch of other treks. Open space, stuff like Worldwide Telescope. There's a ton of software you at home can check out, dive into, and explore. And if solving those same kinds of problems as Dan is an exciting thing for you, this might be something you want to look into. Planetarium field is an exciting one to be in, I can say for sure. But with that, I think we have shot well past our time limit. Dan, thank you so much for joining us here for our Cosmic Conversations. Any parting words?
Just in general, museums are closed right now. The American Association of Museums has actually just released a report recently that says about 30% of museums are not expected to reopen after the COVID crisis. So, if you feel as I do that museums provide a valuable service to society, are an important part of how we as a society reflect on ourselves and tell future stories, do what you can to support museums in this time, and we hope to see you when we can reopen again.
Indeed. One of the most exciting, fun parts of working in a museum is getting to see our guests. So we really cannot wait to see you. But thank you, Dan. Thank you all for tuning in. Stay happy, stay healthy. And from all of us at the Morrison team, thank you for joining us. Have a great day.